We're going to look at Chapter 3, Probability. Chapter 3, Section 3.5, Solve problems that involve the probability of two events. In this lesson, we'll look at distinguishing between independent and dependent events, and we will use conditional probability to calculate the probability of dependent events. Let's recall that probability is the ratio of favorable outcomes to the total number of outcomes possible. So we have the number of outcomes favorable to A, the number of outcomes, or the number of outcomes of what we want, over the total number of outcomes possible. Independent events, the probability of two independent events occurring, the probability of A and B, is the probability of A times B. So recall that independent events are events B does. The probability of event B does not depend on the probability of event A. For example, the probability of rolling an even number on a die and choosing a face card in a standard deck of cards. The probability of an even and a face card is the probability of an even times the probability of a face card. The number of even numbers on a die are 3 of 6, which is equal to 1/2. The number of face cards in a standard deck of cards are 12 over 52, which gives us 3 over 13. When we multiply the probability of an even by the probability of a face card, we get the probability of an even and a face card, which is 3 over 26. Independent events, if the probability of event B occurring does not depend on the probability of event A occurring, then the two events are said to be independent. Dependent events, if the probability of one event depends on the probability of another event, then these events are said to be dependent. Let's look at an example. What is the probability of selecting 2 diamonds from a standard deck of 52 playing cards? If the first card is not replaced, and this is important, if it's not replaced, then that indicates to us that this is dependent events. The first card is a diamond, and there's 13 diamonds over 52 total cards, which will give us 1/4. The second card, which we've already chose a diamond, leaving 12 diamonds left, and leaving only 51 out of the 52 cards left. So we take the probability of getting a diamond and multiplying by the probability of getting a second diamond, and we get 3 over 51. This is conditional probability. The probability of an event occurring given another event has already occurred. If event B depends on event A occurring, then the probability that both events will occur can be represented by the probability of A and B is equal to the probability of A multiplied by the probability of B given that A have already occurred, or the probability of B minus A. So let's look back at that example again. What is the probability of selecting 2 diamonds from a standard deck of 52 playing cards? If the first card is not replaced, and once again this indicates dependent events. The first card, which we will call the probability of A, is equal to 1/4. Then the probability of B getting a second diamond, given that A has already occurred, meaning that there's no diamonds, there's only 12 diamonds left out of the 51 total playing cards, giving us 3 over 51. Let's look at another example. A survey was conducted, and 91% of Canadians own a cell phone. Of these people, 42% own a smartphone. Determine the probability that any Canadian would have a smartphone. So the probability of having a cell phone is 91%, or 0.91. The probability that you own a smartphone, given that you have a cell phone, since you have to have a cell phone in order to have a smartphone, is 42%, or 0.42. The probability of owning a cell phone and it being a smartphone is the probability of a cell phone multiplied by the probability of a smartphone, giving that you have a cell phone. That is going to be 0.3822, which is 38.22%. Let's have a look at another example. Joey's lacrosse team has a 60% chance of winning on sunny days and a 70% chance of winning on rainy days. Joey has a game tomorrow and there is a 40% chance of rain. What is the probability that Joey's team will win? Well, the probability of Joey's team winning when it's sunny is 60%. The probability of Joey's team winning when it's raining is 70%, or 0.7. The probability that it will rain tomorrow is 40%. Therefore, the probability it will be sunny tomorrow is 60%. The probability, now Joey's team can win when it's sunny, and his team could win when it's raining. So the probability that he will win and it's sunny will equal 0.6 times 0.6, which equals 0.36, or 36%. And Joey's team could also win when it's raining. So the probability of Joey's team winning and it's raining is equal to 0.7 times 0.4, which is equal to 0.28, giving us a total of 0.64. Because he can win when it's raining, the probability of him winning is equal to, he can win when it's raining, or he can win when it's sunny, which gives us plus 0.28, 0.64, or 64% chance that Joey's lacrosse team will win tomorrow. Here is a similar example. Curie likes to jog. On hot days, he is 15% likely to jog. On cold days, he's 40% likely to jog. It is 30% likely that it will be cold tomorrow. What is the probability that Curie will jog? If you wish, you can pause the clip and attempt this question on your own. I will continue with the solution. So the probability that Curie will jog and that it's hot tomorrow, given that it's hot, is equal to 0.15. The probability that Curie will jog and it's cold is 0.4, or 40%. There is a chance that it will be cold tomorrow. It's a 30% chance. And the probability that it will be hot is equal to 0.7. Therefore, the probability that Curie will jog and it's hot is equal to 0.15 times 0.7. And the probability that he will jog and it's cold is equal to 0.4 times 0.3. And of course, the probability that he will jog tomorrow is equal to the probability he will jog when it's cold plus the probability that he will jog when it's hot. In summary, we have to remember that probability is the number of outcomes favorable to A over the total number of possible outcomes. If two events are said to be independent, then the probability of event B does not depend on the probability of event A occurring. And the probability, how we could calculate A and B occurring at the same time, would be probability of A times probability of B. That's for independent events. Yet for dependent events, if the event B depends on event A occurring, then the probability that both events will occur can be represented by the probability of A and B, which equals the probability of A multiplied by the probability of B given A already happened, or the probability of B minus A.